Howdy. We are going to use Gauss's law to find the electric field near an infinite line of static charge at point P, a distance r away from this infinitely long line of static charge. And we've done this problem before by breaking the line of charge. We actually did it with a finite stick, and then we broke it into infinitely thin little pieces, into infinitely thin little bits of charge dq, and we canceled out all the y components. We added up all the x components, and we got earlier an expression for this of an electric field at this point of 2k lambda over r. We might have had x the other day because we're using x for that distance, whatever your measure of distance is. And again, we're measuring perpendicularly from the line of charge to point P, which we have drawn in the picture over here. And that's what we got by breaking this thing into an infinite number of little tiny pieces of charge dq and integrating and then extending it to an infinitely long line of charge. And we got that. We're going to get the same thing today, but I'm going to, before we do the Gauss law derivation, I'm going to change this by using our new electrostatic constant. Instead of k, I'm going to put 1 over 4 pi epsilon naught lambda over r. And of course, we have a 2 over 4. So if I simplify that, we're going to have 1 over 2 pi epsilon naught lambda over r. This should be what we get at the end based on what we did the other day. I think I told you, though, the other day that by using Gauss's law, we can do this in 3 lines instead of 3 pages. And here's how it works. All right. Our steps in using Gauss's law are, 1, define a Gaussian surface. And the Gaussian surface used, you want to take advantage of the symmetry of this charge geometry. And here's what we mean. I'm going to express this a little bit more than what we usually write down, because you have to hear this. At point P, first of all, what is the direction of the electric field? And you might say, oh, I don't know. I think the direction of the electric field is this way, like so. You might propose that. You might look at this immediately and say, that's silly. Why is that silly? Well, it's silly because it violates the symmetry that we have in this picture. And by that, I mean the following. If I imagine a plane, I'm drawing a green line here across here. If I imagine that green line defines a plane into and out of the board, this infinite line of charge is symmetric above and below that plane, meaning that the line above the charge up here is a mirror image of the line below. And what that means is that if I can somehow magically flip this line of charge 180 degrees around this, I'm now calling this an axis instead of a plane. That's really consistent. Around this axis, you wouldn't be able to tell when you come back and look that anything had changed because the top half and the bottom half are identical to each other. However, if this is the correct electric field right here, when I flip the line, which would look identical, I would also flip the field. Oh, let me flip the field. Or maybe not. Flip! Up, down. Oh, baby. Okay, and so now the electric field would, because you flipped the wire, the field would have to flip too. And so when you came back, you would say, gee, the wire looks identical, but the field is switched. Why? Why would the field, when the charge geometry is identical, why is the field sometimes pointing down at an angle, sometimes up? What that means is that because of symmetry, because this thing has symmetry above and below this axis, the field has to have symmetry as well. What it really means is that the field can have no component in the direction parallel to the wire, because then you would have a preferred direction, up or down. And the symmetry of the situation doesn't allow that. So therefore, the field has to have no component along that blue line. And I'm just going to get rid of that field, and I will draw the correct field. It has to be pointing directly away from. Now, why directly away from? Because this thing has positive charge. Did I say that? I just did now. This linear charge density lambda is positive charge, just for the sake of argument. And so electric fields point away from positive charges, and it has to be radial away. It can't have a component in the up or down direction. And so I know the direction of the field. I also know that at any given point equally distant from the wire as P, so if I put another point over here and call this point X, and that is also a distance r away from the wire, the field there has to be the same strength as at point P on the right. Those fields have to have the same magnitude as each other. Again, because of symmetry. If I were to this time rotate the wire around itself 180 degrees, then these two fields that I just drew at point X and at point P would switch with each other. Yet the charge geometry wouldn't change because this thing has radial symmetry. It's a line, for goodness sake. And so if I were to rotate the wire, the line of charge, you wouldn't be able to tell anything had happened. But if you looked at the fields and they were different, if this field is a big field on the right and the field on the left is in fact a little tiny field, oopsie, I'm erasing, really tiny field, then when I rotated the wire, the little tiny field would be on the right and the big field would be on the left. And you say, oh golly, why did the fields change all of a sudden when nothing changed in the charge geometry? So the fields equidistant away from the wire have to be the same as each other, again, because of symmetry. So therefore, I'm going to get rid of a lot of this stuff. Oh boy, I'm hitting this button a lot of times. Oh, I hit it too many times. Okay, apparently has a memory. And so I'm going to now get rid of stuff that I really don't want. And so now I'm going to do the problem, and I'm going to take advantage of the fact that I know the direction that E points is radial away from the line of charge by symmetry, and the strength of the field E is the same everywhere at a distance r away from that line of charge. Okay, that is what allows me to choose an appropriate Gaussian surface. Remember, step one is choose the right Gaussian surface. And you're going to get to the point where you say, oh, it's a line. I will choose a cylinder. This is why we choose a cylinder. I want to choose a Gaussian surface. And so I'm going to draw it, and then I'll explain why I choose this. The Gaussian surface I'm going to choose is going to be a cylinder. And it is going to have, I'll try to draw this nicely. It's going to have a radius of the cylinder. It's not a cylinder yet. It's a circle. Is r. And it's going to have a height. And this height absolutely doesn't matter. It's going to have a height h. And then the bottom of the cylinder, drawn with amazing 3D perspective, also has radius r. So my Gaussian surface, step one, is define the Gaussian surface. And you have to say what it is, and you have to say where it is. Okay, what is it? It's a cylinder of radius r, length or height or whatever you want to call it, h. And then you have to say where it is. Okay, very convenient word. It is coaxial with the line of charge. Coaxial means they share the same axis. And so we've now defined this cylinder. We've also drawn it, so we're winners twice. And now, okay, so why did we choose that to be our Gaussian surface? It's a nice closed surface. It makes us happy. And we chose it for the following reasons. On the walls of the cylinder, and yesterday when we were reviewing the area of the two shapes that we're learning, that we're using, I said that we're going to be using the area of the walls and the end cap separately from each other for a cylinder. And here's why. When we look at the wall of the cylinder, okay, everywhere on this wall, it's a curved surface, and so I would have to divide this up into little area elements, dA, and all the area vectors for those point out. This is, I'm trying to draw some 3D stuff over here, are supposed to point out, that's the dA vector, directly out of that Gaussian surface. Well, if I look at an area on the right-hand edge, the area vector, so there's a little tiny area vector over here, something like that. The area vector is going to point directly out, radially away from the line of charge. This makes me happy because the area vector where this electric field is pointing out, and you know what's coming up. We're using our surface integral definition of flux, and if the electric field and the area vector are parallel to each other, it means my dot product goes away, and that makes me happy. So that's why I choose this cylinder, because at every point on the wall of the cylinder, E is parallel to dA, and that makes me happy. What about up at the surfaces, the end cap, cap 1, and down on the bottom, cap 2? Okay, these are the end caps of this thing. What about the flux through those? And when I look at the end caps, now I have a different but equally happy situation because this end cap, I'm now looking at the top one, showing an outline in red. That end cap is a flat surface, so the area vector is the same everywhere. It points out of the Gaussian surface. The area vector is up, and I'm going to call this dA. I'm going to break this up into little tiny areas because it suits me. And every little bit of area on the top of that surface has a dA vector pointing straight up or parallel to the wire. But the electric field at this point, because I'm interested in finding the flux through this Gaussian surface. Let's remember what the whole point of this is. I've designed a Gaussian surface, and I want to be able to calculate the total flux through the Gaussian surface. And I'm going to use that and find out something about the electric field. Well, the flux through this surface on the top, at every point along the top, the electric field, remember, is, I did that in the wrong color, and that disturbs me. The electric field along the top at this point is, at that point, is radially away from the wire. We've already proven that. And so therefore, at the top and bottom end caps, at every point there's a right angle between the E vector and the dA vector. And guess what, boys and girls? That means the dot product for those at the end caps is 0. Or in other words, there ain't no flux going through the end caps. There's only flux going through the curved walls of this cylinder. And that makes me very, very happy. So my Gaussian surface, choosing this Gaussian surface, gives me a surface where there's only flux traveling through the curved walls and not through the end caps. Okay, I know we've been going on for a little while, but this is I want us to understand the choice of Gaussian surface. And again, you're just going to get in the habit of choosing the right ones. I want you to know why, man. And so, Isaac, wake up. Thank you very much. Ha, just kidding. So what am I going to do? I've defined my Gaussian surface. Now I'm going to write the definition of flux. Okay. Pay attention, boys and girls, because I try to make this as cumbersome as possible, too. Okay, the electric flux for this Gaussian surface is actually made up of 3 separate fluxes, because I have 3 separate surfaces. It is the flux through the wall plus flux through cap 1 plus flux through cap 2. And I deal with these separately. In other words, I cannot write a single surface integral for all 3 added together because they're all different surfaces. So the caps are easy. So let's deal with those first. And this is true for both caps, is equal to surface integral E dot dA. But for those caps, E is everywhere perpendicular to dA, which we indicated above. Therefore, the angle theta is everywhere 90 degrees, and cosine of theta then becomes arrow 0. And so my flux, there's no flux through the end caps. And so I can say arrow 0, arrow 0. There's no flux through the end caps. All the flux through this whole thing is the flux through the wall of the cylinder. Okie doke. So, more room. So the electric flux through the whole thing is the flux through the wall. The flux through the wall is, okay, I'll just sort of, wall equals surface integral E dot dA for the wall. Okay, again, we want to get rid of the dot product. We want to get rid of the integral. We will every time. In this case, if we go back to the diagram, E is everywhere parallel to dA. So, yes, you will write this every time. dA is everywhere parallel to dA, everywhere on the wall, exclamation mark. And so that allows us to get rid of the dot product. So this is now integral E dA, since cosine of 0 degrees is arrow 1. And now, the other bit of symmetry that we made note of earlier, and you will not have to write a letter describing how you know these things. You can just say by symmetry as though you know what you're talking about. But we also determined that the electric field magnitude is equal everywhere on this wall because we're everywhere the same distance away from the line of charge. And so that allows us to say E is uniform on wall. And these are no longer vectors in this integral. So E is a constant, so I can pull it out. and that's E times surface integral dA. And I don't have to do anything fancy with that surface integral. This says, what do you get when you add up all the dAs over the surface of that wall? You get the area of the wall. So this becomes the total electric flux is E times the area of the wall. And the area of the wall, we came up with yesterday, the wall is essentially a rectangle of length h and width of the circumference, which is 2 pi r. Okay. So now we can do Gauss's law. Gauss's law says the total electric flux is Q enclosed divided by epsilon naught. And, okay, Q enclosed we have to be careful with because we have to know how much it is. So let me actually go back here and say the electric flux is E times A, but A is H times 2 pi r. Okay, so that's the flux, is equal to Q enclosed. Okay, what's Q enclosed? How much charge do I have enclosed inside this Gaussian surface? Well, I have the amount of charge on this much of the wire. And that much of the wire is H. And how much charge do I have on that wire? Why, it's simply, this thing has a linear charge density of lambda. That's how many coulombs per meter times H meters. The charge on this thing is lambda times H. The charge enclosed is lambda times H. And so Q enclosed is lambda times H over epsilon naught. We're basically done because, let's see, my H's go bye-bye. And I bring the other stuff over to the other side, and I get E is equal to, I've got a lambda on, okay, I'll do the 2 pi epsilon naught. I've got a 2 pi on the bottom along with my epsilon naught. So these things can come over here. And then I have times lambda over r. And that is it. And that